Okay, let's start. People on Zoom, again, if you don't hear me, please let me know. Can you hear me now? Yeah, good. So, first, a good announcement. So people are saying, okay, we have too many deadlines. We cannot finish on Thursday. So let's finish on Friday then. Homework. Don't worry about it. Well, the goal obviously is not to, you know, drive you off the cliff with homework. Just help you to learn. So I hope this deadline will work. So what about the office hours? So does anyone want to show up and talk to me today, or one person too? Okay, cool. And then I was planning to move it to Friday because it's the greenish zone on the poll which I created. So Friday will work. Friday afternoon. Okay. So I will do then 2 office hours this week, and then we'll switch to Friday. So you just have to. The new homework will be released again, actually, hopefully today, and hopefully without delays, and maybe tomorrow. What else? And today we're gonna be using a little bit of your laptops because I want to program a little bit in class just for fun, since we learned so much about how to use MIPS and stuff. So after, not immediately, but after we get to this, to the point when we started, let's do it. Okay, thank you. So again, so our topic today is to take a look again at this SPIM emulator. SPIM is MIPS spelled in reverse. And so take a look at a couple of sample programs again and actually code them up, but also take a look at what actually SPIM is running around main and finish this idea of relocation. Remember, we were doing this detour. I said, okay, we need to learn how to relocate the code. And remember, relocation shows up when we link multiple object files together, and we have to pad, essentially, like merge multiple data sections and multiple code sections together, right? And so we have to actually patch some addresses, right? And this was our example, which we were looking at last time. I don't know, like, this should, I don't know, probably better finally after, I don't know, maybe after 5 years of 5 weeks of teaching, I switched up the line. So okay, so what's going on here? Remember, this was our Hello World application, and what we were doing is the following. Sorry, I was actually hoping to use my finger on the screen as a highlighter, but it will probably, I don't know, it works. Cool, amazing. Yeah, so what we're doing here, we are creating a Hello World program, right? That's what we done at the very end last time. Actually, maybe let me share my video. Maybe it's not that important, to be honest. I'm sharing my screen over here. So, but the high level idea is that the program has multiple sections. It has a text section where the function main itself lives, right? Main has to be declared as a global symbol, so the operating system can actually link against it, right? There is no like an operating system for real running in this emulator, but the emulator kind of like fakes it for you, right? And here's the label main and then the code of main. And what the code is doing is that essentially, remember, we have this table of system calls, which this emulator provides, kind of pretending that there is an operating system that can do it for you. And the one which we're using here is print string, right? So essentially, that's the one which allows you to print a string on the screen. Question?
What was the emulator called?
It's MIPS spelled in reverse. So SPIM, SPIM. But don't worry, I will like show you on URL in a second, and we'll install it, right? Okay, so what we're doing here again, so we're using a couple of pseudo instructions, which first, remember the calling convention for the system call is that you use the first register. I mean, using the register, which is used typically for return of the arguments, right? So V0, if you place the number of system call, number 4 in this example, into V0 register, then place an argument to the system call, the string itself, address of the string, into register A0, then you can invoke the syscall instruction, which essentially performs the system call and prints this message on the string. And the message itself is declared inside the data section, right? You just again use a label and then you use this magical ASCII, IZ, and then the string itself, hello world, right? And it ends with the new line symbol, right? So in how we end the program is, again, there is a special system call here, which is exit without returning any arguments. This system call is number 10, right? So previous one was number 4, this one, to print the string. And a correct program would do the same, load 10 into V0, call syscall. At this point, the simulator and also, okay, the program is done, right? And so we ran it last time, and we ran it using this simulator sim. So this is the URL which I'm using. So let me just quickly go there and just start something. So SPIM itself, we first go to the web page of the author. So it was done by a professor at Wisconsin Medicine, Jim Laros, who moved later. He was then at Microsoft Research for some time, and now he moved back to Europe, where he is a professor again. SPIM is a link here on his web page. And this is the simulator. The reason the choice of the simulator is because this is what Hennessy and Patterson kind of describe in their book in the appendix A. So that's why there is a couple of MIPS simulators around, but I decided to stick to the one which book kind of recommends. And so what it says here is that he no longer maintains it on this web page. So please go to SourceForge. Well, yeah, not even the GitHub, but fine. And then if you want to download SPIM, so you click a link. And for me, it was a Debian file for 64-bit Linux. For you, it might be like, depending on what you're running, Windows or Linux. Where do we have? Actually, I was not very impressed that you can quickly get to the Windows version, but you can probably just choose it from here. So you can get this Windows MSI. If you're on Mac, there is something here as well for you. So, right. So this is how you're gonna install it at home, because you will have to. The next homework assignment requires you to submit a program which actually runs on this simulator and output something meaningful on the screen, right? So this is clear. So nothing really is going on here. But what I wanted to show is the following, right? So let me just quickly start the simulator. So make it a little bit more concrete for you here. This is the same hello world on my screen. If we started, I don't know, what is that, Qt. So this is how the simulator looks. So what it shows here is, it shows two things, so text section and a data section of a program, right? And I can switch between them by clicking here. So the user text segment starts at those addresses, right? And we've seen it in the book a couple of times. That's the convention of on MIPS. So they essentially on MIPS architecture, they said, okay, the user program, the text specifically should start at this address, right? So at this address, which is 40000, right? And moreover, the data section, there's also a convention. It starts even higher in the address space. So start at this address. So roughly, I think it's 256 megabytes. We can double check here. Python, OX, this, and yeah, 256 megabytes, right? So that's the layout of the address space. So just don't be surprised that it doesn't start from 0, like I was sometimes telling you. Like it's essentially the same. The linker just linked the program to start from that address, right? Not surprisingly, the data section contains this hello world, right? And if you go for it and decide to check what are those bits, you will find, ASCII characters, right? So like just go to this table and you'll find the same, right? But it shows you here. And the user stack is located at this specific address. Right now it's right now it contains some information, but and I will explain in a second what it is, right? But like it will be growing down from this address, right? But what I wanted to again, so what it does, you can, it shows you all the registers, right? And what if you switch to text here and you say, okay, let's single step. So this is like single step thingy. It will start executing the program instruction by instruction, right? So on your program counter right now, it used to be at this address. Right now it's changed and it highlights the changed registers with red. It points to 400040. 0004, right? And remember, I kept saying all this time that each instruction is 4 bytes. And again, those are the 4 bytes which you're looking for. And again, if you take those, put them into a binary editor, you will see the opcode and stuff. So if you're really struggling with the homework and opcodes and you want to check yourself, well, you can type a tiny assembly program and check what the opcodes will be. Check for the correct opcodes, right? So, but again, so nothing super surprising here. If we run the entire thing like this, it will show us a console, which will print hello world here in the very top. Let me maybe try to make it slightly larger for you, but I'm not sure that I will be able to do that. But let me just quickly check. Probably not. Okay, right. So any questions about it right now so far? Yeah. What's the website? Just Google for Jim Laros and then SPIM, and it's easier. It's on SourceForge. This is the URL.
Also, if you're running Linux, there's a flat pack for it.
Yeah. I don't know what the version is. I didn't even check, but yeah, thank you. So that's the website, and I'll put it online. But if you quickly, I can put it on Discord, I guess. Where's my Discord? Hey, sorry. That's menus. Menus. Come on. Anything with Zoom is surprisingly slow. So how? What do I do now? Mute all. Okay, we can do this. But I actually wanted to press exit. Oh, exit was escape. Okay, so wanted to put it on Discord. Yeah, let me just quickly. That's wrong. That's wrong. That's okay. So I have to. Discord will be useful later on for. Right, put it here. So, but what I wanted to emphasize, again, you got the point. So it shows the registers, you can single step, you can do a breakpoint. So pretty much like any debugger, right? But do you understand how this thing is implemented? What's inside this? What is it we are seeing on the screen, and why we call it a simulator? Why it's something what is worth our time? Who can tell me? What is a simulator? or emulator. Doesn't really matter.
So like at higher level, it virtualizes like when you run a command, it like
No, correct. So it's if you, and again, I kind of encourage to do this later. So if you go to the source code here, you can get to something like a SPIM. Just you can. It's nice to take a look at the C file. Essentially, it's implemented in C, and what it does, it's essentially says, okay, I will take your assembly program in MIPS assembly, we'll translate it quickly into machine instructions, and then we'll be executing those machine instructions. And that's not super hard. Like you can in any of your software development classes, you might get an assignment to build an emulator like that, right? So there will be this fetch, decode, execute loop, right? So I don't see it here, but like if you take a look at the source code, you will see how it runs, right? It runs on x86, it runs on since it's C, right? It compiles and runs natively on my laptop, but it executes MIPS programs, right? Similar to how a real hardware CPU would execute them, right? And it shows you the registers because every time it executes the instruction, right, it can show you something on the screen, right? Okay, so that's clear. What I wanted to highlight is this piece of code, which is slightly larger than your program, right? And so let's get back to this to understand what is there, right? And the question here is, what is it really running before main? So as you can see here, so the main itself is this purple code, right? So this is the two pseudo instructions which were expanded to invoke a syscall. Let me just go back to, oh, actually I can probably scroll through the slides. Might be a little bit faster right here. So your two pseudo instructions are load immediate 4 into register B0, load an address of message into A0, right? And that's what you have here. So load immediate of 4, here the simulator uses the register numbers. So you say load immediate expands into pouring of register 0 with 4 and putting it in register 2, which is B0, right? If you take a look at the table in the book, the register B0 corresponds to hardware register number 2, right? So, and this is a tiny comment which essentially tells you here on the right what's going on here, right? And then the second expanded pseudo instruction is load address of a message into A0, and this is a little funky. So you say, look, my message, if I really carefully look at the SPIM simulator, my data section, right, and is here, and the message is actually should be at this address, right? It's 10010000, right? And here you see something different, right? You see, wow, it's a load immediate of 497. So what do you think is this? Why do we loading? Where's our 1001 and 4 zeros? Where did it go? Say again. The linker updated it? No, that's a great actually like idea. So linker might place it somewhere else, but what we see here in this simulator is actual hardware address where the hardware believes that this is your string. So this is the actual address. So this is memory, right? So all addresses, and it skips all irrelevant addresses, like from 0 to whatever, the start of this text section at this address, right? But those are relevant, and the hardware says, okay, according to the MIPS canonical userland memory organization, the data section should be there, right, at this address. And you would, if I were you, I would say, look, I would imagine that this address, I should see it in the program, right, which I'm running here in the text section. Who can tell me? Where did it go? This load of address of the message. we've been through this a couple of times, right? So, and it's time to kind of, but at this point, it becomes ultimately concrete, right? So you say, well, real addresses, like everything what you ask me on Discord about what's the opcode and what's the jump address, you can decode from this simulator. So what's happening here, remember, it's a TM argument. Like this address of the data section, it's a 32-bit address, right? So it's contains of 4 bytes, right? And 4 bytes, you cannot load 4 bytes with a single instruction. That's why it splits it into 2 instructions. And essentially the split of this load address, which is a pseudo instruction, is it splits into 2. It says load upper immediate. And if you take this number 4097 and plug it into Python and ask, okay, what's the hex value of it? You will see the address what you want to see. It's this 1001. And since it's you loading into the upper part of the register, right, it goes into the top 16 bits, right? And then, of course, what happens with the lower part of the register is it should be zeros, right? And so actually, look, it ORs it was 1, right? Oh no, okay, sorry. It ORs the register into which you loaded it, which is register A0, and ORs it with zeros, right? So it's essentially just like nothing is happening here. So this instruction could be omitted in a way. But what happens is that it actually places it into register A0, right? A1 was probably a temporary register, like this assembler temporary register, right? So we can, again, if you have questions about MIPS registers, you can always MIPS registers. Like something like even this diagram will help you. Open image. Just let's zoom into it. So this register number 1 is this, is this assembly temporary register AT, right, which I was mentioning. That assembler can use it at its own discretion to like expand a single pseudo instruction into a chain of actual MIPS instructions, right? So any questions about what's going on right now? We were looking at main. Remember, that's what we were trying. We were trying to understand what is this green code before main. And I was just going through main and just pointing out those interesting details, right? So at this point, you do the syscall and it will print this message on the screen because everything is correctly initialized in registers, right? Any questions about those pseudo instructions and expanding of them? Okay.
So if we have the 4i, we have a
wait, you're saying how we shall represent numbers in assembly? You don't even have this number, right? That's okay. Hold on. So that's what I wanted to show you. So in assembly, it's just the label, right? So it's completely hidden from me. And I'm pretty sure that a good assembly will provide you a syntax for choosing any base. So you can use hex, decimal, or binary, similar to C, right? So you can, OX will give you a hex, and I'm pretty sure that this assembler will do the same if you really need an address, right? But in this specific example, you don't even need the address because it's solved by the assembler underneath for you, right? So it just, inside the data section, you declare a label message, and then it automatically tracks where the message is placed in memory and then correctly links the code correctly, so it uses the correct address, right? The fact that the simulator itself uses a decimal number versus a hex, I don't know if it's configurable. I'm pretty sure you can click a button somewhere to say show everything in hex or something. There was another question. Yeah, that's a great question. So I don't really know. So maybe, so just poke at the menus and maybe, I mean, but again, first I was very surprised when I opened it, but then I decided, okay, maybe it's even better for you because this is, again, this ultimately concrete diagram. And if you take this number and split it into those like opcode, register, 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 shift amount, and so on, like then you will get this number, exactly this number 2, 0, and stuff like that. And 4 is an immediate constant, right? So this is an immediate, obviously. Right, so that's kind of funny that, again, so we started kind of very, very abstract, right? And it was, for a while, it was maybe not clear how it even runs, but this is finally becomes concrete. And I wanted you for at least a second to look at this concrete figure to match, right? And x86 works the same, by the way, if you worried. I mean, the instruction encoding is an order of magnitude harder because x86 is so like broken. Not every instruction is 4 bytes. Some instructions are 1 byte, some are 7, some stuff like that, right? Typical size is 5. But yeah. So, but you can always like either like good disassemblers, they show it for you and you can read up manuals, right? Any other questions about it? Oh, good at this point. So, okay, what do you think is happening here? So why are we running this green code even before the main starts running? Because as I was saying, so this is your jump and link instruction, and it shows you the address, right? It shows you the address which goes directly to 24, which is here, right? But if you, again, if you very, very carefully decipher this opcode, you will see, again, you will see what it really means. So like, and it's relevant to the homework. So if you're struggling with the homework, you can type in a couple of instructions into this emulator, and you will get the answer for real. Modular, the fact that emulator can be buggy as well, but at the level of our class, it's not buggy, so it will show a correct thing. Yeah, go ahead.
How do you actually like open text files?
To go on this thing, it doesn't have a text editor. So here you have to, what I did, I can show you again real quick from the console. And despite the fact that I'm using like a graphical version of this Qt SPIM, I just passed a file. If I don't pass a file and just start the Qt SPIM, I just say file, load file.
So you just need to put it
up, sorry. Yeah. And I like here, like I was using Vim for quick editing, but I as well kind of say, okay, let's go and use Visual Studio Code because it has, for you, it's probably like easier. And for me, I mean, not really easier, but okay, right? So just, that's your Visual Studio Code thingy, right? Kind of easier. Yeah, go ahead.
So I installed it.
Sorry, like, can you say this again?
Yeah, so I just installed it's down the road. I'm trying to find it. It's not recognizing it. Is there a particular
so on Windows, you probably have to patch the like. Are you running Windows or Linux? Yeah. On Windows, you're running this. I would assume either PowerShell or you're running their original shell, and you have to patch your path variable to make sure that it's visible in the path, right? So on Linux, a lot of it is automated. I mean, I'm not an expert on PowerShell, but from the days when I was running Windows, just patch it, or just click the graphical icon on Windows. I mean, if you, I agree, everyone should. I mean, my students who run Windows, they still run PowerShell, and yeah. Okay, something I forgot what I was trying to ask. To say there was a couple of questions. Okay. Right. So what I was like this is a mysterious code, and I wanted to explain this green thing. So any guesses? What is that? What is running before main? I was talking about jump and link, and yeah, again, go ahead and like double check this constant is 9. Why is it 9? And say again. I'm sorry. Where are we supposed to go? No, I'm asking the question. My real question is this. We talked about the program, right? We understand that this is what we wrote. This is what we wrote in the assembly. One would expect that main is the very first thing which starts running, right? Like intuitively. Agree with this or disagree? I am showing you the fact that simulator, in fact, runs a little bit of this code before it even jumps to main here, right? That's the jump to main. The question is that what is this green stub of code? Do you understand the question now? Okay, cool. So what would you, can you guess? It's possible to guess, it's a little unusual, but you can guess by looking at this assembly. Yeah, go ahead. You know, it already uses stack pointer in the very first line, right? So apparently stack pointer is actually set by the operating system. And we will come back to it in a second, but it does something, right? So you guys not much C programming, because maybe C++, yeah, go ahead. It's what? It tries to do something with the command line arguments. I agree, so this is close to the real answer. So remember that in C and C++, the signature of main is actually this. So main takes 3 arguments. So it takes argc, an integer, which is the number of elements in this second array, which is array of pointers to argv, right? So you can pass like a number of command line arguments, like you said. And according to the standard, it also sends has a pointer to array of strings which contain the environment, right? And if you print this environment, if this is the program which essentially takes this NVP pointer until it becomes null, the last element of this array is null, and just prints every element of this array. This is something what you will get on the screen. And when you like it will show you the default shell, which has been bash, the term which we're using, and stuff like that, right? So, and that's the standard, right? And you say, look, my main should correspond to this signature. And this is exactly what they're doing here. So they are essentially saying, okay, right now I have, my goal is to start main. And remember the calling convention, main expects that it will have 3 arguments into registers, into registers A0, A1, and A2, right? Right now, the operating system creates those arguments on the stack, right? Because you can place them somewhere in memory, but a logical and a typical convention, natural convention is to place them on a stack. And remember, I was showing you the data segment of a stack. And if you start scrolling here, you will see those environment variables, at least for my system. So home, a boards of yada, 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 right? So this is my environment. So if you're very curious about it, if I type env, the command which shows it to you, this is it. And so that all of this nonsense was passed to SPIM as well, according to the standard, right? And so again, I wanted to make sure that you understand what is there on the stack and why we're running at this tiny prologue. Let me just quickly explain again the prologue instruction by instruction. So right now those arguments are on a stack. So argc is at the very top of the stack. That's why they say, okay, let's use offset 0 and place this into the register A0, right? SP, since argc is 4 bytes on a stack, the next argument will be, what do they do here? They add immediate to stack pointer, so they just essentially, add immediate to 4 bytes to stack pointer, place the argument into A1, right, register, and this is argv, and NV pointer is their 4 bytes of A1, which was just computed here in the previous instruction, and we place it into A2, right? Since argc is the number of arguments, right, and it's right now into register A0, we multiply it by 4 to get actually the actual pointer to the NV environment pointer into A2 here. So, right, so it's multiplication by 4. because you just keep those. And then you can jump to main. This is essentially prologue. And here the epilogue, if something goes wrong, it will invoke the exit system call. If suddenly main exits without invoking this, if you forgot to put the exit system call in it, it will just correctly finish here. Any question about this? Questions about this prologue?
It seems like it's not working.
Are you running it on your own machine and it's not working?
Yeah.
Let's do it. Let's take it offline. I'm okay to take a look at after the class, but it's just try to follow what I'm saying right now, and then let's install this SPIM later. So this prologue is called C runtime CRT0, and if you ever curious about what's going on there, you can look it up online. But this is the essence. And it can be on a real program. You know, the C runtime might, for example, invoke constructors, right? So in C++, if you have a static constructor, something has to invoke it before even jumping to main, right? And I mentioned that like early in the class, but now it again becomes kind of concrete. In C, there is also a way to declare a constructor, surprisingly. So for example, if you have a logging library and you say, look, I have to open a logging file before even jumping into main, because maybe the first line in main logs something into that file. So there is a way to provide a pragma directive to C to say, okay, call this function from the C runtime, right? So that's again and it happens really on like x86 machines as well. So on real things which you're running, it just gets a little bit more complicated. But at least you get the point that something might run before main even. Question? Back to main, back to this node, right?
Yeah, the bottom, yeah.
That's a good question. So you at least assume that main correctly implement the calling convention, meaning that if you call main and it returns to the address, to the instruction which follows the invocation of main, right? So like any other function, if this convention is broken and you just you hand coded or forgot to return, then you're on your own. The simulator will run forever until it hits an exception and then exit. So, but assumption is that this is a well-formed code, which is generated by the compiler or by a knowledgeable programmer, developer. Any other questions? I think I've seen something. No? Okay, good. Yeah.
Does the exit syscall make the jump back to some register, or I would expect there to be a jump at the end?
No, at this point, syscalls are kind of like services provided by the operating system. And when you say exit, the interpretation of this call is that I'm done running. So please terminate the program, deallocate all the memory which was allocated for this program and never come back to it. And this is typical, like when you program main function, you never call the exit syscall, but really the C runtime was calling it for you from underneath. Otherwise, your main runs forever, right? And your program keeps spinning for time doing something, right? But this C runtime or similar, the prologue and epilogue is generated for every program which you invoke. Anything else? Good. Okay, so we good. So we did this. Remember, I jumped into real programs while doing explanation of relocation, right? And so let's finish this detour just for a sec. And this is the source code of or instructions machine code, which got generated from this assembly file. And if I ask you what needs to be relocated here, which lines will require special treatment? And again, it's kind of easy to check because if going line by line, you can quickly find the addresses, the absolute addresses, right? And you have to like, so which one? Jump into main clearly has an address right here, right? And again, going back quickly to the homework. Who can tell me jump is a relative address or an absolute address? Absolute, I agree. Remember, branch was relative because it's within a subprogram. jump and link is absolute address, right? So I agree with this, that we are actually using an absolute address, and this address, because the address which is shown here, maybe it's just a debugger which like resolves it for us. And we really have to think about what's sitting here in this immediate address area, right? So I agree, this has to be patched. What else? What load upper immediate? Correct, right? So load upper immediate uses the address of the message, right? Oops, sorry. And this message might be moved in the data section, because when you're merging with a library, maybe the message gets placed after all the symbols or the global variables which the library is using, right? So in fact, I kind of claim that this one has to be patched as well, because it ORs with 0 right now, but it's not guaranteed that it will have a tail with the lowest 16 bits zeros, right? The address of message, which contains two parts, the upper part and the lower part, both of them can change, right? So we don't have this guarantee. So both of these have to be patched by the linker. What else? Maybe actually nothing else, actually. I don't see anything else. So that's it. So like global address of message, global address of a function, right? So, but kind of again, natural and very, very concrete at this point. I kind of gave you the high level vision for, or like understanding for what needs to be patched. And if you ever need to check, just look at the machine code. You already have the kind of the gist of it. You understand what to look for. And after that, you just say, okay, look, I got it. So all the stack related things don't have to be patched, right? So the stack pointer is initialized by the operating system. It can be anywhere in memory. It's always relative, right? So all these offsets are relative to the register. Remember, I was also saying that we're using the GP pointer for pointing into the data section. And it's a little surprising, but GP is not used on this system. I don't know why. So if GP would be used here, so then you would still have to patch the offset because you know, like within the GP, you could have possibly messages moved, but at least don't get surprised if on some real MIPS machine, you will have a GP here. Okay, good. Okay, so this is kind of fun because you now can read real MIPS programs, right? And I kind of argue again that you now understand how to load a program because you've seen it all. And I'm not saying that, you know, it's like it's 100% knowledge, but it's close to it, right? So you understand, and it's empirical knowledge because you can look at this SPIM program in memory and you can guess, okay, look, there is a stack, there is a data section, there is a text section. They have to show up somehow, right? And this is exactly what's happening when the operating system loads a program, like on Linux or in my operating system class, a 2 operating system, which we're using x86. So you essentially take a header of the executable file. This header will contain information about the sizes of the text and data sections, right? Operating system will create a virtual address space because, well, I don't know, we haven't talked about what virtual address space is yet, but imagine it will do some reservation of machine resources, memory resources, right? Then the text and a data section will be copied into memory, right? And from file. And if you have a page table, again, don't worry about it. If you don't understand what it is, then the page table will be created. Then, of course, since you say, okay, I need a stack, you will set up correctly the stack pointer to the stack. And since we've seen this environment variables argc and argv, you say, well, we'll set up arguments on the stack. So this prologue kind of teaches you that this has to be on a stack. And it says, okay, initialize GP pointer and FP. FP we haven't covered yet, but GP we covered, but this program somehow doesn't use GP, but uses a stack, right? And then jump to the startup routine. So startup routine is not even main, but in a file, in this header file, there will be an offset within a text segment, which is the entry point of a program. Typically has a start label. right? And you jump there, then you create this arguments correctly from the ones to point correctly to the stack, and essentially call main, right? When main returns, do an exit syscall. So the user who runs main doesn't have to worry about the exit syscall, and partially because the exit syscall might be different on each operating system. You can provide it as a library call, I guess, but that's not how it's done. Okay, so again, kind of understood how we load programs in memory, not us, but operating system, which again, I invite you to take an operating system class to understand it completely. Okay, so no magic. So cool. So kind of peeling layer by layer, we got to the MIPS, we understand what's going on. Okay, now fun part, laptops, right? So let's try to write some of those programs. The first one is A plus B, so which reads two numbers from the console and add them. So what I suggest to use as a collaboration tool, which I honestly never used before. And where is it? It's one of those. It's the one which actually allows us to type the code of a program together. Let me just quickly find it though. Like, I have to go through all of my wonderful slides. This one. So the website is called REPL, I guess. Somehow can't click it. Please click it. Come on. Really? Beauty of Zoom. Let me just kill all of it. We don't need any of this, any of this. This is REPL. So it's a website, replit.com. I don't know, replicated. I don't know, has anyone used it in previous classes? It's a collaboration tool which allows all of us code this program together. You done it? No? I never done it myself. So that's what we're gonna do here is I share the link to this template by inviting people on Discord. That's the URL. Where's my Discord here? Another half an hour to search for the Discord. Let's open it again. I'll share it on general. So everyone is on Discord. I can share it on Piazza if you don't not on Discord. Let's do this. General. Okay, that's it. So just click this link and tell me if you can open the template. So what I'm trying to do is essentially, this is how we start, right? And essentially that's the source code of a template of a program which we want to write. So essentially, again, we have a text segment, which right now is empty, like nothing is here. But we have a global main label because we always know that main has to be there. And we have a start of the data segment where we know how to write some ASCII characters, right? And our goal is essentially, let me just sketch it for you here. So, oh, someone is doing it, cool. So read A from console, then, read B from console, then add them, add A plus B, and then print out the result on console. And again, so do you think I know the syntax? No, I don't. So I encourage you to, let's, for example, start with this one, read A from console, right? So I'll do one for you, and then whoever is coding with me can fill in the rest. Let me go here. Oops, sorry. So I kind of remember that we need to do a syscall. I know that we have to load immediate into register B0 because this is where the syscall argument is. I don't remember the syscalls, obviously. So I will go ahead and quickly open. Okay, everyone's here. Cool, everyone in Discord. MIPS, or even like SPIM, because SPIM is specific syscalls. And there's documentation online, and this is what I suggest you do during your homework. Don't get, so it says read string. So syscall number 8, and it says A0 has to contain a buffer where we're going to read. A1 is the length of the string of this buffer. Scary, but let's try it. Now let's start with printing a string. Printing a suggestion is easier, right? Than just always then just reading it back, right? So this is a, let's just add a comment, read A from the console. First, suggest to enter A. This is load immediate into register. Let me just answer a question. A0. We do something like a message, I don't know, message A, right? And here I can add something like message A, suggestion, enter A, right? Good enough. So this, okay, question.
Where's the Discord?
What's the Discord?
Yeah.
It's on Piazza. Invitation is on Piazza. I didn't create it. One of your classmates created. Are you good, or shall I post it on Piazza as well? Maybe someone can help. Okay, so this looks correct or incorrect? My sequence for a syscall. So I claim that it should message A, and if a little ugly, let's do it this way, cleaner. I don't know if it allows underscores and labels, probably. Looks meaningful. Can someone check? Like the way to check, let's copy it into a file. Maybe even this one, so index file, copy, file save as, A plus B. Okay. Let's do wide here so we know what it is. And my wonderful QT SPIM, A plus B live. If we open it here, board, let's run it. Let's see what it tells us. Lame. Why is that? That's single step again. 428. So 428. And what is this? My non-instruction. Does anyone know? Let me maybe clear it again. The simulator. Console is empty. Maybe you can quickly spot a problem for me. I don't see. Okay, syntax error. Message A is not okay. So let's quickly patch it up. Message A, let's do it this. Apparently, there are no underscores in labels, right? Agree with this? Let's run it again. Still, load immediate. So what am I doing wrong? So load immediate is the wrong syntax. Can someone help me? Load address. Hold on. Load address. Load address. Load address. Now at least it's not complaining. We're running. It says at least enter A. I forgot to say exit, right? That's why it says, okay, at some point it reached 34. And it says, okay, 34 is not really an instruction because who knows, maybe there's some invalid opcode placed right after that, right? But okay, let me just fix it up here in this live coding environment. Message A, someone already fixed for me. Load errors, yeah, cool. So how about someone will fill the prompts for B, and maybe we can try to do a trick for how to load the, okay, a little bit hard. So it's a read A from the console, right? What's this call is for read? 12, okay, so let's, hey man, like who's like editing, like someone is real crazy here. Live editing, so message is here, syscall is here, right? Read A, so again, so we do like load immediate into V0, right? And what do you say, 12? 15? 8. Okay, and then we say, what's the syntax for the syscall? Again, I don't remember them, obviously, and I can't really easily get here. So the read string, A0 is a buffer, A1 is a length. The question is like, where will we get this buffer from? We're not reading, hold on. We're not reading strings, we're reading integers, which is easier, right? So it's just 5. So yeah, just read something and it will return me into V0, right? So syscall number 5, and I do syscall, and now I say that I'll put a comment V0 V0 contains A, right? Okay, someone can do quickly, let's do collaborative effort. Someone does read B from the console, and someone does the addition. Imagine, I don't know, you do that for a sec. Let's have fun. We still have time.
Oh, yeah, edits.
What?
Oh, yeah, edits.
What could be?
How do we add edits to this REPL which I shared? Supposedly, since a bunch of people joined, then they have write access to this
URL which I shared on Discord. If you click on it, you just be able. It's kind of like a Google document thing. Shall I send you put a URL on Piazza, or are you on Discord as well? Not yet. Let me do Piazza quickly. And Piazza. Post. This, no. Where's my REPL? So at least it's fun. So invite. Okay. Post my notes. What is it? Statistics. Posted a note in Piazza as well. So if you only have access to Piazza, just reload Piazza. Okay, so where are we? Hey, stop. Someone is running cell. Guys, who's working on this? Okay, there is move. Oh, somebody did a message for B. That's cute. Yeah. So we're going a little hard that we are stepping on each other's toes, right? Because move it to the instruction. Yeah, that's a good idea too. I'm here. Yeah, I know.
Okay.
Yeah, we're trying to add A and B together and print it out on the screen again. Okay, hold on. Let's stop for a second and listen for questions. So what is A? It's like in any high level language, you say, let's read 2 numbers from the console. One number is A, another number is B, right? And so we learn how to read A from the console, right? In these lines 13 through 15, right? And then we're gonna read B from the console. It's a user provided input. And then we will add them together and print out the result on the console, right?
What was the move command?
Move is a pseudo instruction which moves from one register into another. Under the hood, it expands into addition with 0, right?
Okay, so it's assigning V0. Like, is it assigning V0 the value of S1?
No, it's moving the value which is currently inside V0 into S1.
Okay, so V0 is the output.
Correct. Okay, so what's going on here is, look, we read
There it goes. There it goes. Moves too fast.
Let me clear up. Clear up. This is called. Here we read what. No. Here we go. Right. So this is no one is touching this one. Right. So kind of. So although someone erased the number of the system calls. So which one? Print is 4. Right. So here we have to place 4. And load address of a message into A0 and then do a syscall. This is how it should be. So this is the sequence which prints out A0 on the, which prints out the message A on the console, right? So which intent here is to prompt the user to enter A1, right? So back to your question. So what happens here is, here we want to be getting, we're just outputting this message on the console. In the second system call, which reads an integer, and the system call is number 5, right? And let me, someone is aggressively, oh no, not aggressively. So, oh man, come on, slow down. I don't know, I never use this collaborative tools, but someone is insisting on like deleting glide. So the second sequence, we say line 14, please be started. If you took the system call number 5 for us, we do it 0. And it's the syscall. The syscall takes an input from the user, an integer. User types 577, for example. And this result shows up back in B0 again. So that again. Who is? Let me just again clear up this one. I'll try again. And move seems to be correct. If it works, I never. So right now, V0 contains the input, and this looks sane to me. Like lines 13 through 16 look meaningful, right? And here. Yeah, you will get used to them, and we can put comments. I'll just move this one. I wanted to put the comment here. This one we can delete. I don't know, like, right? V0 contains 8 at this point. Not 8.
So this one is like add S1. V0 and then 0 and then
right, absolutely right. You're right. So thank you for putting it in. So okay, so where are we? So we suggest to enter B, message B. That's correct. Read B from console. Okay, yeah, let's do it as well. Someone is cleaning it up.
LI is pseudocode.
Load immediately. So it allows you to load a constant. And the trick here is this. LI is very, very useful because you don't have to split a 32-bit constant into upper and lower. It just does it for you.
So it just loads a constant into the register.
Correct. Loads a constant into the register.
Oh, so you don't have to use add.
Correct. Or you don't have to use load upper immediate. Otherwise, you have to, if you have a 32-bit constant, you have to split it into the upper 16 bits and lower 16 bits, and then load upper immediate, and then OR with the lower part.
Oh, so that's like pseudocode. And you need the pseudocode because constants in add 16 bits.
32 bits. In add immediate, you're right. I forgot exactly the number of bits, but yeah, less than 32.
And so you would need to like somehow But so like you need to add a median to one register, add a median to another register, and then add those two registers.
Correct, correct. And you can maybe shift them to make sure that you shift by 16 to get into the upper part, and then OR them together, right? Yeah, or add them together.
All right, so oh yeah, you have to shift them.
Yeah.
Yeah.
Or you can use an instruction which is load upper immediate, which loads into upper 16 bits right away.
So one way is add immediate to both of them, and then take one of them and shift it by 16.
Correct.
To the left.
Yeah.
And then you add them together.
Correct.
And then
or them together because you know that they don't overlap. So you can do it. Yeah, I think OR is faster. It's one cycle. Addition is actually one cycle as well, I'm pretty sure. Okay, so are we there? It looks almost there. Oh wait, someone tries to assemble it in a shell. No, hold on. I don't think Replit supports MIPS, and I didn't have time to figure out how to do this support. So I don't think you can trivially compile it here. Although I'm pretty sure it's doable. You have to install this Qt SPIM or like a console version of SPIM, and then it will be actually able to run this. But I haven't done it. So again, but that's a great idea to do this. Okay, so ready? So can someone say on Discord? Okay, let me just read over it to double check that we are there. Okay, main guys okay, let's just listen to me. Like maybe let's stop coding for a sec. So main labels are canonically shifted to the left. It's easier to read them this way. They comments are, you saying that this is a comment? It's not a comment. So in assembly, the comments remain, I think, those things, right? This is the comment. So load immediate, syscall, read A from the console. I was putting 2, but you don't have to put 2. V0 contains this. In MIPS, I'm not sure that slashes work as comments. So those should work. Move S1, V0 goes here. That looks okay to me too. Suggest to enter B. Yeah. Load again, syscall number 4, B message, syscall, read B from the console. Again, offset them correctly like this. Syscall, again, move into S2, correct. Add A plus B, just do an addition, that's correct as well. You can use a temporary register or S1. By the way, do you remember the calling convention? We are brutally breaking it because, just hold on guys. Remember the calling convention that if you use registers S1, S0, and so on, you have to save and restore them, and no one is doing it. It's okay because no one is calling main, but still, if in a homework I ask you to build a recursive function, you need to make sure that you preserve the calling convention. So I would suggest to either use temporary registers instead of S0 and so on, or like make sure that you save and restore them. Okay, print result back on the console, A1.
So we want to change all the S's to T's
probably, but let's not do it now. But this looks good enough to me. Let me pick it up, go to my Visual Studio, delete all this nonsensical stuff, save it, and let's restart the simulator. Again. Syntax error start text. So remember, the comments cannot be. I was saying that the comments cannot be slashes. So this is a comment in MIPS assembly. Let me do it again. Data message. Okay, let's take a look at what it is. I don't know myself. So Oh, data is a, wait, hold on, this is important. So data is one section. You cannot say you have two data sections. Theoretically, you can have multiple sections which have specific meanings, but like the way the simulator handles data, it's there must be a unique data section, right? So this is correct. Let's do it again. Seems to be running, at least not complaining that we have syntax error. Enter A, let's say 4, enter B, 6, output 10. Success, guys. The first MIPS program after, what is it, like after, yeah. No, I still kind of, it's all like, it's a joke, I understand, but I think you learn enough. So and this, the reason I wanted this live demo, so you guys are not worried when you start your homework, you're ready to kind of roll forward. You see how it works, how like a group of people can edit it together, and it's, you know how to use system calls, data section, stuff like that. So I think, you know, that month was spent, you know, successfully. So we learned how to do it. I almost didn't code anything on this one. So I probably will stop here. So the next homework is for real, writing those programs, but you know how to do it now. And the complicated part will be recursion. So essentially I will ask you to build functions which recursively call themselves. I will first ask you to build a simple function and then a recursive function. So make sure that you understand the calling convention and preserve everything. Okay, thank you. We forgot to add the exit system call. That's why it's crashing right now. Not crashing, but complaining.
You mentioned moving the homework to Fridays. Does that include this homework, or is that starting with the next homework?
No, this one.
Okay, so this one will be due Friday instead of Thursday?
Yeah, not tomorrow, but Friday. Okay. And the next one will come up with a date. Okay. If you want Friday, we can do Friday. I wanted to avoid Friday because on Friday I want to have fun.
Okay, that's fine.
That's why I said Thursday. So I'll try to do Thursday again.
Okay.
For next week, so you can have fun on Friday versus later until midnight and coding.
Thank you.
So what are these syscall commands actually doing?
Well, let me just finish here.